All right, today's the day where we're going to look at the examples in the homework from last week, and we are going to try to figure out a shortcut for what happens when you take the derivative of a number times x, and that x is raised to a power. So example 2 from last week is exactly that kind of polynomial. It's a number multiplied by x raised to a power. We took its derivative, and we found out that we got the derivative to be 6x squared minus 10x. There's a pattern in there. It is not very obvious, but it is there. If you look at the blue terms and you look at the green terms, perhaps you have a little itch in your brain that you're like, I think I maybe see something, but that's probably not it. But we're going to dissect this a little bit and talk about it. So there's something very consistent that happens when you take the derivative of something of the form a number times x to the power. There's a relationship basically between that power on the x and that coefficient a. And we're going to dissect that example to see what it is. That was the original function. That was a derivative. That was with us doing all that limit of x plus h minus, that whole thing. Now, one thing that you maybe didn't think about this way, and I'll make you think about it this way right now, is that 2x cubed in the beginning, if that was the only thing in the function and we took its derivative, then we would have had 6x squared. So in a way, that 2x cubed became the 6x squared in the derivative. If the only part of the function had been the negative 5x squared, and that's all I had to take the derivative of, it would have become the negative 10x. So the negative 5x squared turns into the negative 10x. And if the only part of the function had been that 1, you'll see over here I didn't put any corresponding pink stuff because that 1, it went away. And by it going away, it basically becomes, 0. So can you see any kind of relationship between these numbers and these numbers? Something consistent that happens with this and with this to get us this number and this number? Does that same rule apply? Like whatever you can think of that might use these to get this and this, does that same rule apply to use these to get this and this? It might be helpful if I threw in some extra notations. If I have a constant, anytime I have a constant, not even if it's just 1, every time you have a constant, you can think of that constant as being multiplied by x to the 0 power. And you can do that because x to the 0 power is just 1, and 1 times anything is itself. So how can I use this negative 5 and this 2 to get this negative 10 and this 1, this 2 and this 3 to get this 6 and this 2? Okay, maybe you can see it. We're going to look at the other examples from last week to help us solidify. So I don't know if this was example 1 or 2, but x squared became 2x. Negative 3x became negative 3. Does your rule still work? This is the one we just dissected. So the 2x cubed becomes a 6x squared. The negative 5x squared becomes a negative 10x. The 1 goes away, becomes 0. The x cubed turned into 3x squared. The negative 4x became just another little negative 4 with no x at all. And the negative 1 went to 0. These constants, I just wanted to put another reminder. It's kind of an awkward place, but it's in my slideshow now. Every time you have a constant, you can think of that as being multiplied by x to the 0, because that's the same thing as 1. And then in the derivative, those constants turn into zeros. So that might help make that rule that you're seeing a more consistent rule applied to anything like that. But what about these other examples? We had a 1 over x, a 1 over x squared, a square root of x, and a cube root of x. The 1 over x's derivative became negative 1 over x squared. It doesn't seem like it's following the same rule. 1 over x squared became negative 2 over x cubed. What? How do I take a cube root of x derivative and get a 1/3 x to the 2, or like 1 over 3x to the 2/3? That doesn't make any sense. It actually does. It's the same rule. If we rewrite these guys as a number times x to a power. None of these right now are written as a number times x to a power, but every single one of these expressions I can rewrite this way. 1 over x can be x to the negative 1, and its derivative, which we found as negative 1 over x squared, I can rewrite that as negative x to the negative 2. So if I look at this portion of f of x and its derivative, isn't that the same rule that you might be seeing? 1 over x squared, which can be rewritten as x to the negative 2, I can rewrite it as x to a power. its derivative, which I found to be negative 2 over x cubed, we can rewrite that as negative 2x to the negative 3. So the same rule that turns x cubed into 3x squared, isn't that same rule taking x to the negative 2 and turning it into negative 2x to the negative 3? The square root of x, which I can write as x to the 1/2. The derivative, that was this. I can always take this second portion, just this x to a power. I can take that part and pop it to the top with a negative exponent, right? If you have some constant over x to the m, you can rewrite that as constant times x to the negative m. For example, if you had something like 7 over 3x to the 9th, you can take this portion that's raised to a power and make the exponent negative and put it in the numerator, and then this could be like a coefficient in front. The 7 over 3 becomes a 7/3. So 1 over 2x to the 1/2, that could pop to the top and become 1/2 x to the negative 1/2. So isn't that, oh, that's not what I want to do. Isn't that same rule that's taking 2x cubed and turning it to 6x squared, taking x to the 1/2 and making it 1/2 x to the negative 1/2, taking x to the 1/3 and making it 1/3 x to the negative 2/3. I'm going to shut my mouth and sip my coffee while you chew on this for a minute, and then I'm going to totally spell it out if you're not. If it's like, it's a lot to see. So if you're not quite seeing it, because let me just be quiet for a minute and sip this coffee. It's a big gulp. My goodness. So if you think you have it and you're not sure, or you're not seeing it at all, what's happening is we're taking this power, like let's look at the 2x cubed to the 6x squared. It's that power on x multiplied by the coefficient to make the new coefficient, and then decrease that power by 1. So if I wanted to find this derivative using a shortcut, I can do 3 times 2 to get the new coefficient of 6, and then decrease this power of 3 by 1 to get squared. So 2x cubed becomes 6x squared. This negative 5x squared, 2 times negative 5, makes the new coefficient of negative 10. And then I decrease the power on x by 1, so x squared becomes simply just x to the first power. We never write the first power. We don't do that. And if there's a constant, if you take the derivative of a constant, it's just going to go to 0. But that's, if I want to think about it in terms of the rule, that constant could be x to the 0 power. 0 times anything is 0, and then it doesn't really matter what happens next because it's going to be zeroed out anyways. Same thing down with these crazy guys. 1 over x, I can rewrite that as x to the negative 1. So to find the derivative, this power times the coefficient. And now if there's nothing written there, we assume there's a 1 there. So negative 1 times the coefficient of 1 makes a new coefficient of negative 1. Decrease that power by 1, it becomes negative 2. Negative 2 times this coefficient makes negative 2 as a new coefficient. Decrease that power by 1. Negative 2 take away 1 makes negative 3. X to the 1/2, the coefficient right now is 1. So to get the new coefficient for the derivative, multiply 1/2 times 1. So I have a coefficient of 1/2. Decrease that power by 1, it's negative 1/2. Same thing down here. X to the 1/3. So take that power times 1. That gives me 1/3. Decrease that power by 1, it's negative 2/3. So this is called the power rule for finding a derivative. It works for any expression where it's a number times x raised to a power. Sometimes you have to take expressions like the ones down here and you need to rewrite them so they're x to a power. Obviously, like a common mistake here is to maybe like try to make this derivative 2x, but we can't do that because if you have stuff in the denominator or if you have stuff under a radical, you've got to rewrite it. So it's just x to a power, x to a power, x to a power. It cannot be in the denominator, can't be under a fraction. It's got to be like that. And when you do that, the derivative will be power times coefficient is the new coefficient, decrease the power by 1. It's a shortcut. So today's homework, I want you guys to do 2 things. I want you to do them by the definition. So the definition is when we use the limit as h goes to 0 of f of x plus h minus f of x all over h. I want you to still use that definition. But then I want you to verify your work this time by checking it against the shortcut rule that we're using here. Good luck, you guys. Hope you're enjoying this as much as I am.